I received too many emails about how we can manage the data in Bayesian network analysis, especially when we have a very complex network where we need the large amount of the data to process. Now, one of the method through which we can reduce the number of the probability data is called divorcing parents in Bayesian network. So let me take an example and then I will explain you what I'm trying to explain in this tutorial. So for example, I have a network. Let's say I have a node B, I have a node C, and I have a node D. They are connected to node A. It is a directional link. That's what make it is a Bayesian network, and it is acyclic. So this is my Bayesian network, for example. Now, if I want to find out what are the number of probability values that I need to populate in the conditional probability table, so the formula that we use is number of probability values that is equals to our number of the states, and we take its power to the number of the variables. So if I want to find out for this network what will be the number of the probability values I needed, so let's say these variables, each variable has a 4 states. So 4 raised to power the number of variables. So A, B, C, D, we have 4 variables. So 4 raised to power 4, when we solve it, we get a number of 256. So this means in order to solve this Bayesian network, we need 256 probability values that needs to be populated into the conditional probability tables. So as you can see that this is a very complex thing. It is a very hard to get this much data. However, what we can do is we can use this method of divorcing parents in Bayesian network, and we can reduce these number of probability values. How we work on that? So for example, let me go down here. So this was my network B, C, D, and A. Let me redraw this and then I will explain you the method again. So this is my B, this is my C, this is my D here, and all of them are connected into the A. This network, I just take an example. Your Bayesian network will be different from this, of course, but the method and concept will remain the same. So in divorcing, what we do basically, we break down some variables and combine them into another variable, or intermediate child node is introduced. So let's say over here I introduced a variable, B remain the same, and then I have the C, I have the D, and this is my A here. Let's say B is going into the A, and C and D, I choose another variable. Let's say we give it a name of S or any variable, and now the output of this S, that will become input for A. So S become the parent of the A. Now this variable which we just introduced, the S variable, let me delete. Okay, so this variable S that I just introduced, it is called a synthetic node. This is my synthetic node. So this node is basically child of C and D, and it become the parents of my node A. So this was my initial network, and this is my network after I applied divorcing methods on Bayesian network. Now, what is the advantage of this? If you recall, for this network, I need almost 256 probability values that needs to be populated into the conditional probability tables for this network. However, for this one, let's see how many we'll need. So let me choose a different color here. Now, if you look on this network, I have values for two networks here. One is basically B, A, and S, and the other network is S, C, and D. So if I want to calculate how much probability values I will need, so for example, for B, A, and S, I have, again, the formula remain the same as I explained you earlier. Let me go back again on the top and I can explain you the formula. This is the formula I'm going to use here. The number of the probability values I want to find out, and it is the number of the states raised to power number of the variables. So let's apply this again into this. So for this network, number of the states for B, A, and S. So the number of states remain the same, which are 4 basically. Now the variables involved are 3 variables. I'm talking about B, A, and S. And for this network, which is C, D, and S, the number of states remain the same, 4, and the variables are 3, B, C, and S. And because I want to see the combined number of probability values, I just take sum of these two values, and that turns out to be 64 probability values. Now, as you can see, from 256, I have reduced my probability values to only 64. And all I did is just introduced a synthetic node between the variables, and then I solve it as a regular Bayesian network. Now there are certain rules how and where we can introduce synthetic node, and that's what I'm going to explain you. This is one of the examples and the definition of the divorcing from the literature. This is taken from the Jeremy Kane work on the use of the Bayesian network for planning improvement in natural resource management. The definition says that divorcing is a technique for simplifying the structure of a Bayesian network. It involves grouping a number of parent variables so that they fed into an extra intermediate child. Now, this is one of the example for our study today. Again, this I took from the literature. Jeremy is the reference for this. So, as you can see that I have the type of the fertilizer, I have the amount of the fertilizer, I have the timing of application which are going into the yield, and irrigation scheduling, irrigation application, soil type is going into the yield. So if I look on the conditional probability tables that we will need for such network, it will be a very complex. So each variable has a state of 2, let's see, and now I need to take the power of number of the variables. So I have 1, 2, 3, 4, 5, 6, and 7. So 2 raised to power 7. How many I get here? 128 probability values I will need for this network, and it will be a very complex thing to solve this. Instead, what we can do is we can combine all these 3 similar variables. As you can see, this is the type of the fertilizer, it is the amount of the fertilizer, and timing of the application. So I can introduce an intermediate synthetic node in between here, in which I will take the input from these 3 and one output can go into this yield. I will show you in few minutes what I meant to say. Again, irrigation of scheduling, irrigation of application, and soil type. These are very similar kind of the variables. Again, I can develop an intermediate node here, synthetic node, take all these 3 input into that node, and then take out one output to the yield. What I'm saying is, this is what I'm trying to explain you here. As you can see, Here, type of the fertilizer, amount of the fertilizer, time of the application. So we introduced a new node which is called fertilizer application, and we are taking all input into this. And again, from the bottom, irrigation, soil type. So I gave it a name of the crop water application, and then similar to the original network, they are going into the yield. Now, what is the advantage of this? The advantage is that for this network, if you recall what I did previously, I need 2 raised to power 7, which was 128 probability values for conditional probability tables. However, let's see how much we need for this network. I have this, and I have this part of the network. So for here, I will see how many are the states. 2 raised to power, I have 5 variables, and this turns out to be 32. Again, for the blue section, I have 2 raised to power 5, which is 32, because I need for the combined network. So if I add up these two, I will get 32 plus 32, which is 64. So as you can see, from 128 probability values that I was looking for in conditional probability tables of this whole network, I have reduced it to 64 values. So that is what is the advantage of divorcing parents in Bayesian network. Again, there are some limitations in this Bayesian network. For example, sometimes variables are very critical to our main variable. For example, let's say the soil type here is very critical to the yield. In that case, we cannot use an intermediate node to connect it with the yield. In that case, we will have to use it directly with the yield. Let me erase this, and I can explain you a little bit more clarity. So what I'm trying to say is, if for example soil type is very critical to the yield, we cannot take this link, it will be directly going into the yield. Now the second important point is, of course we are introducing new nodes here. This is a new node, this is my new node. The structure of the Bayesian network will be expanded. However, given that we have reduced our number of probability values needed for the network, which was 128, and now it is 64 only, it is believed that the computational task will be very much reduced, and collecting and using those probability data will be much easier and convenient. Now, one thing I want to mention you, if you are interested to read more about this, this is the book Statistics for Engineering and Information Science by Jansen, Bayesian Networks and Decision Graphics. You can read this book if you go on page 61 to 62. There you will be able to find out much more information about this. If you're not able to find these pages, or if you're not able to have the book available, you can email me, and I will try to share these selected pages with you. I hope this helps, and if you have any questions, feel free to email me. Thank you.